Imagine computers that could unlock secrets.
Yeah.
Secrets of materials that don't even exist yet.
Or designing drugs with, pinpoint accuracy.
Exactly. We're building AI that learns like us. Things way beyond our best supercomputers now.
That's the huge promise of quantum computing, isn't it?
It is. But here's the flip side, the monumental challenge. Actually building these things,
Yeah.
making them reliable, making them big enough, it's been incredibly tough.
One of the biggest hurdles in science, really.
So today we're diving into something pretty exciting. A real breakthrough, it seems, from the University of Sydney.
Ah, yes, that Nature physics paper. It's making waves.
Right. Highlighted by SciTech Daily, too. It looks like a genuine leap forward in making these machines, well, real.
It tackles some of the biggest roadblocks head on.
Our mission here is to unpack this, especially how they apparently made a universal logic gate, like a processing unit, inside just one atom.
Which sounds almost like science fiction, but it has huge implications.
Yeah, and what that actually means for quantum tech going forward. Because the big idea, the core insight we want to explore, is how this could slash the number of physical quantum bits, the qubits you need.
Which directly hits that scaling bottleneck we've been facing for years.
Totally. It seems like it could change the game. So let's get into it, unpack how this sort of Rosetta Stone for quantum computing might be bringing practical, large-scale machines closer.
Sounds good, because the potential is just, well, it's staggering. Revolutionizing medicine, materials science, finance, you name it.
The vision is huge, no doubt.
Yeah.
But getting there, that's the grand challenge, as you called it.
It is. How do you build something not just powerful, but big enough and maybe most importantly, reliable enough?
Because these quantum states are notoriously fragile.
Precisely. That's the heart of the problem. Qubits are incredibly delicate. When they do their work, these quantum operations, they're constantly hit by random errors. Think of it like static on a radio line during a really important call.
Makes it hard to trust the result.
Extremely hard. You can't easily get stable, meaningful answers out of your calculation. It's just this inherent vulnerability in any quantum system.
Okay, so researchers obviously knew this,
Yeah.
and they've come up with ways to fight it, right? Error correction.
Yeah, that's the standard approach. The basic idea is you encode the information you care about across multiple physical qubits.
Okay.
So some of those qubits are essentially acting as guards, detecting and correcting errors happening to the others.
So you get a more stable, kind of averaged out qubit, a logical qubit.
Exactly. A smaller number of robust logical qubits that you can actually compute with reliably. That's the foundation.
But that sounds like it could get complicated fast.
And that's where it becomes, well, what people have called an engineering nightmare. Because for any really useful calculation, you need a lot of these logical qubits. But the more logical qubits you need, the exponentially more physical qubits you need to back them up to do all that error correction.
Whoa, exponentially.
Yes. The numbers just explode. It's not a small overhead, it's massive. And that sheer resource demand has historically made building truly useful quantum computers seem almost intractable.
It really does sound like a nightmare. You need reliability, so you add more physical parts, but then those parts add complexity and potential errors.
It's a vicious cycle. This massive overhead for error correction, that's the barrier, and that's exactly the challenge this Sydney team tackled.
Okay, so it's this huge scaling problem. You need tons of physical qubits for just one reliable, logical one. But there was a theoretical idea floating around to help with this, wasn't there? These GKP codes?
That's right, Gottesman-Kitaev-Preskill codes, GKP. They're really quite ingenious, and that nickname, the Rosetta Stone of quantum computing, it's actually pretty fitting.
Why the Rosetta Stone? What's the connection?
Well, think about the original Rosetta Stone. It let us translate ancient Egyptian hieroglyphs because it had the same text in known languages. GKP codes do something similar for quantum information. They provide a way to translate the smooth, continuous, analog nature of quantum states, which are naturally prone to small errors drifting all over the place.
I like the wobbliness.
Exactly. They translate that into something more discrete, more digital-like, specific states that are easier to manage.
So it takes the fuzzy quantum information and makes it sharper, more like digital bits.
That's a great way to put it. It's like turning a blurry analog photo into a crisp, pixelated digital one. Once it's in these discrete GKP states, it's much easier to see when an error has occurred, like a pixel being the wrong color, and then correct it.
Okay, so it makes spotting and fixing mistakes much easier.
Dramatically easier. And it also turns out to be a very compact, a hardware-efficient way to encode these logical qubits.
So the theory was great. GKP codes promised a way to use fewer physical
A
qubits.
huge promise. For years, they offered this compelling theoretical path to reducing that massive hardware overhead.
But there's always a but, isn't there?
Yeah. Well, the but was that actually doing it, actually implementing and controlling these GKP states in a real physical system, that was considered incredibly difficult.
Why? What made them so hard to handle?
They're just very complex quantum states themselves. They require extremely precise control to create and manipulate without destroying them. So for a long time, they were sort of theoretically beautiful, but practically out of reach.
Okay, so this amazing theoretical tool, this Rosetta Stone, was sitting there, but nobody could quite figure out how to reliably use it in the lab.
Pretty much. We knew what it could do, but not quite how to make it work consistently.
So what did the University of Sydney team do differently? What was their breakthrough?
This is where it gets really interesting. The researchers at the Quantum Control Lab there, Dr. Tingray Tan, a Sydney Horizon Fellow, and his PhD student, Vasily Matsos, who's the first author on the paper.
Right.
They managed to take GKP codes from being just a theoretical concept, almost a mathematical curiosity, and made them a physical reality. They actually built and controlled them.
Wow. Not just simulated, but physically made them work. How? The paper mentions doing it inside a single atom.
That's the truly remarkable part. They constructed an entangling logic gate, a fundamental building block for computation, using the properties inside one single atom.
How does that even work?
They used a trapped ion, a single charged atom of ytterbium specifically, and they figured out how to tap into and precisely control its natural vibrations, its harmonic oscillations.
So the atom's own jiggling?
Sort of, yeah. It's like they choreographed the atom's internal dance to perform these complex GKP operations. Dr. Tan put it very clearly. He said, our experiments have shown the first realization of a universal logical gate set for GKP qubits.
Universal gate set.
Yeah.
That means they showed they can do all the basic operations needed for any quantum program, right? Like the quantum equivalent of A and D or not gates.
Exactly. They demonstrated the fundamental toolkit. They can manipulate single GKP qubits, or they can entangle two of them together, which is crucial for computation. They've shown the whole set works using this GKP encoding.
And the efficiency Vasily Matsos mentioned. That sounds incredible. Storing two logical qubits in one atom.
Yeah, he said, effectively, we store two error-correctable logical qubits in a single trapped ion and demonstrate entanglement between them. That is a huge deal for hardware efficiency.
Because normally you'd need, what, dozens, maybe hundreds of physical qubits for just one logical qubit with other methods?
Easily, sometimes thousands, depending on the error correction code and the quality of the qubit. So doing it with two logical qubits in just one physical atom, that completely changes the resource calculation.
How did he manage the two qubits part? Using vibrations.
Right. So Matsos managed to entangle two different quantum vibrations of that single atom. Think of the atom moving in 3 dimensions. Each direction of movement, described by quantum mechanics, is like a separate quantum state or mode.
Okay.
He essentially used two of these vibrational modes, these different ways the atom can jiggle within its trap, as distinct logical qubits, and then entangled them within that same single atom.
That's wild. Using the atom's own internal movement modes as qubits.
It's definitely a milestone. It rethinks how you even package quantum information.
So practically, how did they trap and control this single atom so precisely? What does the setup look like?
Well, they use something called a Paul trap. It's basically an electromagnetic cage that uses oscillating electric fields to hold a single charged particle, like their ytterbium ion, very precisely in space.
Okay. Does it need to be super cold, like some quantum computers?
Remarkably, no. This setup works at room temperature. They use a really complex array of lasers, carefully aimed and timed, to cool the atom initially, and then to manipulate its quantum state, its vibrations, to create and control these GKP codes.
Just lasers and an ion at room temp. Sounds simpler, but I bet the control needed is intense.
Oh, absolutely. It's precision engineering at its finest. And that's where the software component was also crucial.
Ah, right. You mentioned software earlier.
Yes, they collaborated with QCTRL, which is actually a spin-off company from their own lab.
Yeah.
QCTRL developed specialized quantum control software.
What does software do?
It essentially used physics-based models to figure out the best way to pulse the lasers, the best control sequences to create the GKP states, and perform the logic gates without distorting them or letting errors creep in too much.
So it's optimizing the control signal.
Exactly. Protecting these very delicate GKP states while making them do useful work. It's this combination of clever experimental setup and sophisticated software control. It really makes you think. It's not just theory anymore. We're physically engineering these complex quantum states.
Which brings us back to the big question you raised. How does this actually change things? What's the impact on scaling up?
Well, the immediate headline impact is pretty clear. Massive reduction in the quantum hardware required to build these essential logic gates.
And you need those gates for any quantum program.
Absolutely. They're the fundamental building blocks, so making them much, much more hardware efficient is a potential game changer for building bigger machines.
It directly attacks that resource overhead problem we talked about.
Right? Dr. Tan pointed that out. He said GKP codes have long promised a reduction in hardware demands to address the resource overhead challenge. And this experiment, well, it delivered on that promise.
So it's not just fewer qubits, maybe it also suggests pathways to more stable or faster operations too.
That's a really good point. By encoding things so efficiently, it might open doors to different types of quantum algorithms or perhaps allow for deeper, more complex calculations than were feasible before with the same amount of hardware. The stability aspect is key too. GKP codes are designed for error correction.
So demonstrating these universal gates with GKP qubits, it really lays a foundation, doesn't it?
It really does. A foundation, as they say, to work towards large-scale quantum information processing in a highly hardware-efficient fashion. It's not just a neat trick, it's a practical step.
It suggests the path forward might be less about just building enormous arrays of simple qubits and more about really clever, precise control of more complex, efficient units.
Exactly. That's why people are calling it a milestone in quantum technology. It's proof that you can develop quantum logic with far fewer physical qubits, boosting efficiency dramatically.
It feels like it pulls the horizon for practical, large-scale quantum machines quite a bit closer.
It certainly makes the engineering challenge look less nightmarish. It shifts the focus from brute force quantity to intelligent quality and control at the atomic level.
So for you listening, trying to figure out how these amazing machines might actually get built and change things, this isn't just a tiny refinement. It feels like a genuine leap.
It makes the whole endeavor seem more feasible, more practical.
We're moving from a scenario where quantum computers might have seemed too big, too error-prone to be truly useful anytime soon, towards one where the basic building blocks are getting much smarter, much more compact, much more robust.
A more achievable path forward.
So just to recap our journey today, we started with that huge challenge, quantum errors, and the engineering nightmare of scaling, needing potentially millions of physical qubits for useful tasks.
Then we looked at the theory of GKP codes, this Rosetta Stone idea for translating noisy quantum states into something discrete and error-correctable, promising efficiency.
But they were hard to control in practice. Until this work from Sydney, trapping that single ytterbium ion, using lasers to precisely control its internal vibrations.
And entangling those vibrations within the same atom to create a universal logic gate set with unprecedented hardware efficiency. 2 logical qubits in 1 atom.
It's an amazing story of physics and engineering working together.
It really is. And understanding breakthroughs like this, I think it helps you appreciate just how intricate and, well, how clever the solutions have to be to push these frontiers. It's not simple stuff.
Definitely not. It transforms these abstract quantum ideas into something tangible, steps towards real technology.
Finding these elegant solutions, often where you least expect them, like inside the jiggle of a single atom.
It really is elegant.
Yeah.
And it leaves us with a pretty interesting thought to chew on, doesn't it? If the future of quantum computing might rely less on massive construction projects and more on this kind of exquisite microscopic control, this dance within a single atom, then maybe other huge engineering challenges, things that seem impossible today across all sorts of fields, maybe they could also yield to similar kinds of elegant, compact, incredibly efficient solutions if we just find the right way to look at them.
That's a fascinating question. Where else could atomic level control or similarly clever, compact approaches unlock breakthroughs?
Something to think about. Until our next deep dive.